Cast iron piping system, especially in the water feeding industry, for example. Corrosion product when you have scabs, where no other techniques, I will say, unless you use radiography, but no UT, for example, can be used in that case. And PEC is a very valuable technology for scab inspection, and any online systems with ferromagnetic materials. How does it work? So the working principle, here you see a cross-sectional view of a single element PEC probes. So it includes some copper coils that are generating a constant magnetic field pulse. And the goal of this pulse is to magnetically saturate the conductive component that you can see. So here you see the rock wool, and at the bottom the components, the wall thickness of the pipe, let's say. So the goal is to magnetically saturate it using a pulse. What will happen, if we look at the PEC acquisition cycle, it's divided in 3 steps. Step 1, phase 1, we are pulsing, so emitting this constant magnetic field long time enough to achieve a full wall penetration. So that's what we call the saturation, and this will lead to the pulse width calculation. Once we estimate that the component is fully saturated, we will cut off the pulse, and this will generate the eddy current. So this will create an eddy current inside the piece. The next step is the measurement of the decay time of the eddy current. So while the eddy current will vanish, we measure this decay time, and this decay time will be converted into a wall thickness at the end. A short video to illustrate that. So you can see a probe in grid mode pulsing through an insulation with a metallic weather jacket. Magnetic field is penetrating the wall thickness. When we stop pulsing, that's what you can see now. The eddy current will just vanish from the component, and this is the decay time we will be measuring with some dedicated sensors inside the probe. So when it comes over a nominal wall thickness, you see a normal A-scan signal. And the more you come through or over the corrosion area, you will have a faster decay time that will give you a wall thickness average measurement. Some important parameter to consider when talking about pulsed eddy current will be the footprint. So what is the footprint? It refers to the full width at half maximum of the response when you detect a localized defect. To make it simple, it is the width of the signal peak detected by the PEC probe when it comes across a defect, measured at -6 dB, so half point from the peak maximum height. This is what is illustrated on the right side of the slide. What can impact the footprint, or how the footprint is calculated, let's say. It's calculated from the probe size, the probe model that you will be using. Also from the lift-off, so the distance between the component and the probe itself, due to the insulation, for example. And the component wall thickness will also affect the footprint value. This footprint value is important to determine the optimal grid resolution when you will do your scans. And also that will help evaluating the minimum detectable defect size. We used to say that the minimum detectable defect is more or less 15% of the footprint volume. So you have your thickness, the component thickness, you have your footprint, you calculate the volume, and a wall loss of 15% of that volume is something that can be detected with the Pulsed Eddy Current technology. Talking about the minimum detectable defect, what we call the MDD, you can see on the top of the slide, we have illustrated a footprint volume and two different types of defects. So one is deep and small on the left side. On the right side, you have another defect, which is larger, but not as deep as the first one. But in reality, those two defects show the same volume missing, and that will give you the same response. Why is that important to consider? Is that when we talk about accuracy, sizing accuracy, let's say that a defect that will be larger than the footprint will be sized correctly. When a defect will be smaller than the footprint, because we are measuring a volume loss and an averaging value, we will be undersizing. So this is important to consider, and it's not explained in the presentation, but we have developed some tools that comes with the lift called the CWT, the Compensated Wall Thickness Tool, that will help you when you have defects smaller than the footprint to correct the value and limit this undersizing. The PEC signals. So understanding the PEC signal. PEC is sensitive to wall loss. That's what we are looking for corrosion, erosion, and wall loss. But is also sensitive to interfering components. If you have metallic structure, for example, that will bring some mass effect on your signal. And of course, the material properties are important. So the permeability, the magnetic permeability, the electric conductivity of the components will affect the PEC signals. And especially when you have variation across your component, this may lead to some false positive calls. So the sizing algorithm we use with the lift system assume that only the wall loss impacts the signal initially, and that's what you will see on the A-scan signal. Most of the time it's true, but sometimes for some reason you can have residual magnetization, for example, of your component from previous MFL inspection or previous MPI inspection, and this material property variation will not be taken into account on the A-scan signal. So that's why we also introduce two other views, let's say, the Tau-Scan signal and the PermTool, which are two dedicated tools with the lift that allows you making the difference between a false positive and a real wall loss at the end. Another thing to take into account is the context. The context for a good interpretation of the data acquired, it's essential to know it before doing the inspection and also during your inspection. When you are performing your scanning, knowing the context is important because that will shed the lights on the artifacts or anomalies that can be visible or found on the C-scan or on your A-scan signal at the end. The context, what can help you is as-built drawings, asset histories, picture from the fields, for example, to see if you have a metallic structure around your component. Any notes from the technician, knowing, for example, if some other inspection were done on your part with a magnetic technique like MFL or MPI, for example, that might be important to know because that may bring the light on some of the false code that you can get on your C-scan. Your C-scan at the end will summarize all the A-scan, all the data, all the spots that have been inspected across the surface of your component. It will also give you some sizing values, either in millimeter or in percentage of wall loss or remaining wall. And you will also have some warning. So when the system will detect problems like saturation or overspeed or weak signals or saturated signals, it will just highlight that during the inspection live. So coming back to the PEC signal, you see on the right side of the slide, so the same data for the same measurement, the A-scan signal on the left, the Tau-Scan on the right. Those signals, A-scan and Tau-Scan, they contain information that will be related to the wall thickness and the wall loss, if any. The defect size, if you have some interfering components, I was talking about mass effect from a metallic structure, for example, or if your probe comes close to a nozzle, for example, or a flange, you will have also this kind of mass effect. If you are inspecting insulated pipe, it's important to look at the Tau-Scan, for example, to make the difference between the different type of weather jacket. If your weather jacket is made of aluminum or stainless steel or galvanized steel, the view on the Tau-Scan will be different, and that can help catch some issues you can have on your component definition, for example. If you are facing also some corrosion products like scabs or blistering, you will see that from the A-scan and the Tau-Scan curves. And obviously also false positive, that will be seen on the PermTool that we will see later in the presentation. We will start by a presentation of the Tau-Scan and the working principles of the Tau-Scan. So the Tau-Scan is just another representation of the signal, and it's emphasizing the signal decay, in fact. The Tau-Scan view can be divided in 3 parts. So the first part from 0 to 1 CDT will correspond to what we call the infinite wall region. The second part from the 1 CDT to 2 CDT, CDT is for a characteristic decay time, is corresponding to the bending region. And then above 2 CDT, you have what we call the plateau region. So looking closely at the infinite wall, the bending region, and the plateau region, that will help during the data analysis, differentiating or understanding the signal better to make the difference between a real corrosion, a real wall loss, and something that can be induced by other interfering components, for example. I put a link on that slide. I will not open it, but when you will have a copy of the presentation, you will be able to go on our website and look at a short e-learning giving more details about the Tau-Scan with some additional examples. So how to look at the Tau-Scan curve when it comes to the infinite wall, so from 0 to 1 CDT region, this region. So the curve here follow a power law function. It will contain information on the front wall, the material, and the weather jacket. And the slope will be related to the material properties. Okay. So we can consider that for low carbon steel, the slope is almost constant. How that can be used, just for example, a high slope variation compared to the calibration, which you can see in the red signal on your curves, will suggest unreliable sizing. So that will, let's say, conduct the analysts to look closer at the data and look at the overall C-scan and check what can be wrong in that region to make sure if he finally calls a corrosion or not. It will also help this region in particular identifying if you have weather jacket definition error, because we have a delay coming from the weather jacket. If you have an aluminum plate or a aluminum jacket, sorry, stainless steel jacket or a galvanized one, All those three will have different delays that will be taken into account, and it's important to know these values. So it's part of the training that we give when people attend the PEC training. So it's important to look at this. It's important also to know if you have some jacket overlaps, because those jacket overlaps can lead to some saturation and will affect the delay from the weather jacket. So this is what we will look first when looking at the Tau-Scan in this region. The second region, so the bending region from 1 to 2 CDT, you can see here. I don't know if you see the mouse, but otherwise I can maybe, yeah, right here, maybe it's better like this. So here is our bending region from 1 to 2 CDT. This here is important because it will contain information about the defect depth. Here, the distance between the red signal, which corresponds to our calibration on a nominal thickness, and the black line, where we are doing the measurement actually. This difference will be converted into a wall loss. So that will help us sizing the depth of the defect and give a relative sizing compared to the footprint. It will also allow us identifying when defects are smaller or larger than the footprint and also the averaging area. I didn't talk before about the averaging area, but this is something we covered during also the training. An averaging area we consider is almost 2 times the footprint. So considering that a defect is larger than the averaging area, it means that will be obviously larger than the footprint, and then we will consider an acceptable sizing accuracy, a good sizing accuracy with plus minus 10%, for example, accuracy. On the right side, it's an example of a defect that is smaller than the averaging area. You can see here the black line. So let's say because of the slope of this black line, we can understand that this defect is smaller than the footprint and the averaging area. Otherwise, if this defect would have been larger, it would have followed the dashed line that you see, the defect plateau. So if we have something like this, okay, we'll consider a proper measurement. Because of this, here we know that we are undersizing, and then we will have to use the CWT, so the compensated wall thickness tool or algorithm within the LIFT software to help correcting the value and try to get a better sizing with the help of this tool. We've been talking about the infinite region, infinite wall bending. The next will be the plateau region. So the plateau region obeys to an exponential decay. The plateau height will be related to the remaining wall thickness at the end. And looking here at this region, so over 2 CDT, as you can see on the top and on the bottom, will just expose mass effect if you are close to a nozzle, a flange, if you have metallic structure around your probe, around your component. That's where you will see it, and you can, knowing the context of the inspection, avoid false calls. But also, if you have some noise sources, electromagnetic noise, mechanical vibration, for example, will generate noise, as you can see, for example, on the top illustration. So all this will help you improve your analysis. And at the end, of course, the plateau, you will look at the plateau to confirm the validity of your initial setup. Some example in the next slide, just to highlight. So we've been talking about mass effect. This is typical signal you will get on the Tau-Scan when facing some mass effect. So you will see that the black line is almost parallel to the red calibration value, but crossing and exceeding, the slope is higher than the normal one. Saturation also that you can catch in the infinite wall region, all right, can be caused by many parameters, such as jacket overlap, for example. And on the right side, the last example is when you have some scabs. So scab is an external corrosion product that you have to cross to reach the nominal remaining thickness on the component. So this is typical signal from scab. That's all for the Tau-Scan. Let's move on to the PermTool. So on the right side, a typical signal that you can face when you do a PEC inspection. So in red, your calibration signal on a nominal wall thickness, and all of a sudden, you have a signal that comes above the calibration line, stronger signal, which is crossing the calibration signal, and which has a faster slope, a faster decay. So this, at the end, will be interpreted by the software as a wall loss, but we need to be careful here because this can be caused by, this can lead, to false positive call because of property variation, for example, or interfering component. Okay, so difference between a defect right here, isolated defect surrounded by nominal wall thickness, and here something that shows like a defect, but in fact, when we will look further on the PermTool, we will identify it as a false positive. Again, for those who will have the copy of the presentation, click on that link, will take you directly on our website to e-learning dedicated to the PermTool. So, looking at the PermTool, what do we have? We have a view. On the x-axis, we are looking at a normalized amplitude signals in decibels. And on the y-axis, we are looking at wall thickness variation in percentages. And this here is divided in 3 zones. So the undefined zone, you can see in white with a white background. A false positive region that we can see identified in a dark gray color. And in a light gray color, we have a unknown region. It's uncertain. If you have your signal here plotted in this uncertain region, it's difficult to say if your defect is a real true wall loss or is a false positive due to permeability variation, for example. And then you will have to investigate further, especially if you are, for example, inspecting under corrosion, corrosion under insulation. I mean, you will have to remove the insulation at some point and do some additional check, UT measurement, just to check if you have a real wall loss or something else. You can also do, why not, some residual magnetic field measurement to check if you have some residual magnetization there. So here, again, what can cause a false positive when you do PEC inspection? Typically, hard spots, cold working, or residual magnetism, but not only. This can lead you to false positive. If you just stick on the A-scan and the Tau-Scan, you will call a defect, and the PermTool will, at the end, give you a final analysis that you should not call that one because this will be a false positive. So that will help you discriminate between false positives and true wall losses. I hope it was clear so far. We have been covering Tau-Scan and PermTool, not in details, but for the details you have access to the e-learnings for further information. So let's move on and look at some application examples. Here it will be about sphere legs, so corrosion under fireproofing. So the sphere legs are typical carbon steel tubes with a layer of concrete, most of the time with the metallic rebars in the concrete. The codes, API 2218 and the API recommended practice 583 recommends you to survey the fireproofing for cracking, bulging, or rust strains, which will be indicative of corrosion under the fireproofing. Those standards recommend to perform a selective removal of the fireproofing, so you'll have to open some windows in your concrete to access to the pipe itself and make some inspection, some measurement. Okay. But unfortunately, corrosion under insulation does not always display external signs where it is present. And this is where Pulsed Eddy Current can be really helpful for this type of application. You can see here a picture of a rope access job performed on a sphere legs using a PEC array 6-channel probe, the array probe which has a bigger coverage in our catalog with almost 450 millimeter of coverage in one single pass. And on the left side, just an illustration of a component. So a sphere leg made of carbon steel. It's a pipe. It's 9.5 millimeter thick. It has 50 millimeter of concrete insulation, and it also has some reinforcement bar inside the concrete. So based on this, we will scan, and after scanning, let's say we obtain this type of results. This is real work that was done in the field by one of our clients sharing this views. So this is what they gather with the PEC probe. At the end, identify a region of interest at the bottom of the sphere leg, open a window inside the concrete, and finally they found a hole, a true hole, so no more thickness at all in that position. So let's say PEC for sphere legs is very effective technique that doesn't require to open any window, that doesn't require scaffolding, for example, if you do it with the rope access operators, for example. The next illustration will be corrosion near insulation support rings, or what we call ISR. So on some pressure vessels, you may have some support rings just to support the insulation across the full height of the pressure vessel, the insulated pressure vessel. So this is an illustration that you can see here. And if you have any damage on the insulation and you have moisture and water ingress, for example, it's more likely that it will stay humidity or will stay on top of the insulated support ring, leading to corrosion, and this is something we need to catch. But also, this ring is a metallic structure, so bringing some, let's say, mass effect. So we'll have to differentiate the mass effect from the ring from real corrosion at the end. At Eddyfi, we have conducted an experimental test using a lifelike mock-up. So you can see at the bottom a metallic plate with this ring here, and on top of the ring we have a machine different type of defect. So you have a view here with different depth, different wall losses. Okay, we have installed some insulation on top of that plate, on top of the ring, the support ring, and finally we get this C-scan at the end. So if we look basically at the A-scan, where the cursor here is, we can consider a wall loss. If we look here at the Tau-Scan, same. We have the infinite wall and the bending region are giving us some, let's say, acceptable signals. Just the plateau wall is showing something caused by mass effect. And this is the interference coming from the insulation support ring. And at the end, just with those two those two signals, it's difficult to tell if we have a real wall loss or not here. But looking at the PermTool, you can see that we have our views divided in two parts. Part is coming from the defect signature, so the wall loss that we have machined on that part, on that sample, and the rest coming from the support ring signature corresponding to a mass effect. So it's really the combination of the three signals that at the end will allow us to call for a defect and to identify the area of interest with the corrosion for this type of application on insulation support rings. Let's move now to ship inspection. So ship hull or ship deck, both is something that can be easily addressed with the Pulsed Eddy Current technology. Here, coming back to the context I was talking about earlier, we have to take into account thin walls. So those plates usually are not very thick, a few millimeters, maybe to 15 or maybe 20 millimeters in general. Excuse me. Usually we don't have any water jacket. If you look at the ship hull or the ship deck, everything you can find eventually on a ship deck will be a coating, like ceramic tiles, for example, or some, let's say, adhesives eventually. So few millimeters of lift off, which is not that much. But important thing to consider looking at the structure of the ship, we will have interfering component. And we know that because we know that it's made of welded plates. Those welded plates made of carbon steel may have some material property variation eventually. And of course, also inside the hull, we may have some vertical and horizontal stiffeners. So those stiffeners, this is something that will be detected with the PEC, but we can differentiate them from real corrosion. Just before moving to the next slide, here you see a dedicated probe that you can find in our catalog, which is an array probe with 7 channels covering almost 180 millimeter in one single pass. With an encoder, you can use that on a pole and do your scans and collect the data on your deck. But you can also use that on the hull. And eventually, if you are looking for some, let's say, crawler, magnetic crawler to do a remote inspection, PEC inspection on a hull, we also have some dedicated solution, as you can see here. So we have a magnetic crawler with some cameras, and at the front, right here where my pointer is, we see another probe, a dedicated probe for this type of inspection that we call the C300, that we will show more in details on the next slide. So this is the probe that was mounted at the front of the crawler, and that allows to do a scan of a ship hull. What can we see from this C-scan view here? We have some dark blue lines, both horizontal here and also vertical. This comes from the stiffeners inside the hull. And we have area of interest. For example, at the bottom right, we have some interesting area with what we can expect to be a heavy corrosion, maybe 30, maybe 40% of wall loss. And here we have also an isolated spot surrounded more or less by nominal wall thickness. Nominal wall thickness is displayed in blue on the C-scan. If we look here, this here is seen looking at the toe curve and the Tau-Scan curve and the PermTool as a real defect. So this is not material property variation. Here we have, as we have seen before, on the plateau bending region and on the infinite wall bending and plateau region, a nice A-scan signal typical from a wall loss. And when we look at the PermTool, most of our signal is plotted in the undefined region. So calling for a corrosion here can be done and with confidence. In the next slide, here again, so my pointer here, you see the cursor is on top of a stiffener of one of those dark lines that we can see. And this becomes obvious when you look at the Tau-Scan curve. You see that our signal here is typical from a mass effect and crossing the red line with a much higher slope. So nobody will call anything here, but you can identify of course, easily the mass effect regions. The next application we are going to talk about is the FAC application, so for fast or flow accelerated corrosion that you can find on some piping, especially sometime in elbows. So this can lead to internal erosion in the time of the pipe use. So here is an illustration of scan that were done. Okay. And we can see based on the A-scan and the Tau-Scan curve that we have a faster decay on the A-scan. We have something also showing on the Tau-Scan that we have an important wall loss, because here you can see that we have almost more than 50% wall loss in that region. And finally, as the pipe becomes accessible, if you remove the insulation, so on top of the pipe, and can access directly and do some UT measurements, so manual UT or phase array corrosion mapping, it's easy to validate the wall loss at the end. And of course, the UT additional inspection you will perform will give you a more accurate value of for the remaining wall thickness compared to what PEC can give you. I remind you, PEC is giving plus minus 10% accuracy in the wall remaining sizing, provided that the defect is larger than the footprint. Another application example, sorry. So just standard piping in a plant, corrosion under insulation. Here, what we can see is a scab effect. So it's similar to what we have seen in previous slides. So our A-scan is a faster decay, giving us a 50% wall loss, more or less. Our A-scan also, Tau-Scan, sorry, the first region, the infinite wall and the bending are acceptable and showing wall loss. And then the scab product, so the external corrosion product on top of the remaining wall thickness, is giving us this mass effect, okay? But looking at the results on the permeability tool, all our signals are plotted in the undefined region, which can lead us to call a true wall loss here with confidence. This part here is available at Eddyfi. It's a part that was cut from the field with real scab defect. Okay, and we have done on that part some radiography in addition to Pulsed Eddy Current inspection on the scab material. And you can see here that the PEC results are very close to what the RT gave us as a remaining wall thickness. So that means that you can do the inspection here with less issues compared to radiography. Radiography is a good technique, no doubt about this, but it has some, you need to comply with some rules, some safety rules. Usually nobody can work when radiography is performed somewhere on a plant around, I mean, to reduce radiological dangerous issues. With PEC, you can come, you can do your work. If you have somebody else in the vicinity performing other jobs, there's no issue. It's fast technique also. So, and it doesn't require to ask for authorization to bring a source or X-ray tube, for example. So, comparing the two techniques, PEC will give you something very close to what you can get with the radiography, but with less difficulties to implement. Again, one last, that will be the last, by the way, the last example I will show this morning. A-scan curve, already something weird, a signal starting over the red calibration line, also crossing the section with a faster decay. So just based on this, there's something that can need to investigate. Looking at the Tau-Scan, you identify directly at the beginning of the signal some saturation here. And even if the plateau looks good and the bending region looks good, but here definitely something wrong with this saturated signal. And looking at the PermTool, all our data, all our points are plotted in the dark gray region. And so this is typical from a false positive, so there's no corrosion here. Maybe a hard spot. If you have something like this in the field, basically this will not be something that you will call on your final report and identify as a wall loss, a corrosion or erosion, etc. But you will need to identify this region as suspicious and start further investigation. So maybe have the insulation removed and do some UT just to confirm that it's a false positive. You can call a false positive, by the way, if you want in the report, just to highlight that. That can be a helpful reminder. Close to the end regarding that presentation, we have 10 minutes left, so I will go very quickly on the conclusion. So complex inspection may lead to challenging analysis, of course. If you have scabs, if you have material property variation, if you have interference from external metallic structure, nozzles, flanges, scaffolding, for example, why not, if the scaffold is too close from the pipe or the component. So this makes your inspection more complex, and you will have to take care, to be careful with your analysis. For that, you will need to take into account the new data representation that we have introduced with the latest version of the LIFT software, which are the Tau-Scan curve and the PermTool in addition with the A-Scan. This is part of the training that we give. We have an online training for this, and this will boost your analysis confidence at the end and help you differentiate between false positive, and real wall losses, real corrosion, real erosion. And the goal of this is what, at the end, we need to have a safe and cost-effective asset operating. We want to reduce downtime as much as we can, and we need to enhance the reliability of the asset. And using Pulsed Eddy Current can help in a faster manner reach that goal at the end. Thanks for listening to me for those last 50 minutes. I'm ready to hear any question you may have.
I unmute you, so if you have a question, you can ask the question or use the chatter if you're more comfortable with. Well,
I'm just adding a short comment, Larbi. Thank you so much for this very nice presentation. A bit high level, I will say, because more things about the physics and about the application. Just to add also that in this case, I think in quite all the cases you show, we need to use a lift GDA, correct?
That will be, you will have the same thing. Yes, obviously, because you see that we have a nice resolution, and when you use a dynamic probe, you can collect more data and have a high resolution scan. So collecting almost 3 times more data than normal grid mode. If you do grid mode, you have to consider the footprint. The best resolution you can get will be half of the footprint, and this will be mandatory, for example, to do to use the CWT, the compensated wall thickness tool at the end. But for sure, whenever you have the ability, the possibility to use a dynamic probe or dynamic system, you will save a lot of time, and you will gather more information in the same amount of time, and you will have a better sensitivity, better accuracy, and better performances.
And about the winning of time, yesterday I was discussing with some customer about Leaf G and Leaf GDA, and could you give me an idea? And we were speaking about the sphere legs.
Okay.
Could you give me an idea with and without the PEC probe?
Basically, what I know from this application about sphere legs, initially sphere legs were a lot of people were using the former PEC system from decades ago called the Incotest system, and the Incotest system is just a single element probe, and you are using that in grid mode. So you have a grid which is drawn on your sphere legs, and you take spot measurement. In fact, like when you do a UT spot check, you just do some spot measurement. But if the corrosion appears between two spots, you will miss it, basically. With the Eddyfi system or the Eddyfi probes, the initial probe also were used in grid mode. And then we have introduced a few years ago a dynamic scan. So you can, instead of taking spot measurement across a grid, you can just run your probe along a line and collect all the data. So that will help you collect more data. Even if you don't want to inspect the full circumference of your sphere leg, at least you can do maybe north, south, east, west lines, and that will give you a better idea than what you get before with the grid, of course. But imagine using the array probe. So the array probe, the PK6, is covering, as I said, 450 millimeter in one single pass in dynamic mode. So here you have, imagine from the top of the to the bottom of the sphere leg, you are running that probe covering 450 millimeter in one single pass. So depending on the diameter of your leg, it will take you several passes, but you will collect the full circumference, the full surface, 360 degree, the full length of the leg, or at least the leg, the part that is acceptable. In a short amount of time, you will have a full C-scan that you can plot on a 3D view if you want to have a 3D view. And from there, following also that sphere leg in the future with the same type of scan, it will be easier to compare the C-scan from 3 years ago to the C-scan you will collect next month, etc. So there's, I think, a real benefit because using this PK probe, the PK6, will not leave any dead zone in your sphere leg.
It's not only
some spot check. If you do spot check,
not only a question of time. It's also more definite. You cover.
You have a better resolution.
Okay.
You will have a better resolution, and then you will leave no blind spot. If you do spot check, if you do a manual measurement on a grid mode, you may have some area which is remain not inspected in the dark. When you do an array, a dynamic measurement with the array or even with a single element probe, you will have data all along and no dark zone or no.
Merci, Larbi. Okay.
You're welcome.
Okay, good.
I see that we have a question about the download link for the presentation. So we will definitely. We have the details. I don't know, Aurélie, if we can on our website where with the video will be provided, if we can add the link. Otherwise, we will send it. I will send it individually.
What was the question, Larbi?
To provide a download link for the presentation.
Oh, okay.
I will send the video to all people who register the webinar. So you will have the
and then
video,
you will have
and
you can add the link. Okay, I will provide the link.
Well, thank
you
so much, Larbi.
As
for the presentation.
usual, when you will receive the link on the webinar recorded, don't hesitate to ask because maybe you have some additional question. So don't hesitate to contact Larbi or Aurélie or myself to get more information, please.
Well, we will conclude the webinar. Thank you so much, Larbi, and the
Thank
AEND.
you. Thanks everyone for attending.
Thanks everyone for attending. Our next webinar will be in October 23 about oil and gas solution. We will provide you more the subject details later. Gracias Larbi y AEND.
De nada.
Y el próximo webinar será en octubre 23, Oil and Gas Soluciones. Muchas gracias a todos. Erosion, ¿tiene algo?
Yo creo que está cada día un poco mejor por el español, Aurélie. Dunque, casi ya me puedo marchar tranquilo porque después de cubrir todo. Thank you for your participation or for the organization, Aurélie. Thanks again for the AEND. Thanks for all of you who spend your 1 hour time to follow all this webinar. And I think that with the recorded webinar, we will send also a short survey, a short question. We would like to know if some of you get maybe wishes or a theme or subject that we will go more in deep in November. That's it for my side. Thank you. I'm here in Porto. It's a disaster about the fire, unfortunately. So just thinking about all people from Portugal also who get this difficulty. Thank you for all of you. Thanks.
Thanks, everyone.
Thank you. Bye-bye.